Hi everyone, this is Mrs. J, and today we're going to talk about derivatives and rates of change. Alright, I have a quick warm-up for you guys, so please pause the video and give it a try. Alright, go ahead and check your work here. So for part A, what you can do is you can combine the two rational expressions into a single one, and then when you do that and you simplify, you are left with finding the limit as t approaches 0 of 1 over t plus 1, which you can just use direct substitution to get the limit of 1. For part B, if you rewrite this to change the negative exponents into rational expressions, you'll see that direct substitution gives us 0 over 0, which is an indeterminate. So one of our strategies is just rewriting or simplifying. So we can combine the two fractions in the numerator, and it leads you to this, which you can keep simplifying until eventually you can just do direct substitution to get the limit of negative 1/9. And then for this one, the part C is definitely a challenge problem. So this one was pretty tricky, I think. So direct substitution gives you the indeterminate. So different ways you can approach this, but we can try multiplying by the conjugate, which gives you an expression that looks like this. Now, if you rearrange the terms in the numerator to group the terms with square root of x next to each other, and then these two terms, you can factor within these individual binomials, giving you this. This factors to square root of x times 1 minus x squared, which is the difference of two squareds, giving you that 1 plus x times 1 minus x. Here you can factor out the GCF of x, and you'll see there is a common factor of 1 minus x that you can simplify out. So that leaves you with this expression, which then you can evaluate the limit just using direct substitution. So again, this is definitely a challenge problem, but if you worked through it and you got the answer, good for you. All right, so today we're going to start talking about this concept of a derivative, which ties into the rates of change of different functions. So first, I want to talk about the concept of just average rate of change of a function between two intervals. So here we just have some function. I'll just call this function f of x. And you'll see that I just have 2 points. I have a and x. So let's say I want the average rate of change between a and x. So here, while we can use little dotted lines, we know that this is f of a, and then this right here is f of x. So the average rate of change is really just the slope between these 2 points. So actually we can connect these 2 points to make a linear equation. This would be called a secant line. So if we want to find the average rate of change between 2 points, we just need to find the slope of this secant line. And we all know how to find the slope of a linear function. It's just rise over run, or y2 minus y1 over x2 minus x1. So here I can see that y2 is f of x, y1 would be f of a, and then we have x2 minus x1, which is just x minus a. So again, that's just simple slope formula. So we're finding the slope of the line that connects these 2 points. That would be the average rate of change of this function over this interval. Now, what if we wanted to find the instantaneous rate of change? So let's say we want to find the instantaneous rate of change at point A. Here we will be looking to find the slope of the tangent line. So that's the line that only touches our function at one point. So this is the same function, but this would be our tangent line. So we need to find the slope of this line. So we already talked about how to find the slope of the secant line. So let's see if we can kind of connect the average rate of change to this instantaneous rate of change. So you'll notice here that the secant line had a larger slope than this one. But let's imagine we slowly moved our x value closer and closer to our a value. So let's say instead of x being here, what if we made x maybe this value right here? And you'll notice that if we connected those two dots, okay, this secant line is a little bit closer to our tangent line. So then let's imagine we keep moving x even closer and closer. So let's say we move x here. So it's getting really close to our a value. So that would give us this. So you can imagine the closer and closer this x value gets to a, the closer and closer we will get to our tangent line. And in fact, if you can imagine a scenario that you're essentially moving x so close that you're almost exactly at a, or we could say that x is approaching a, you would eventually end up with this tangent line. Well, luckily we know how to have a value approach another value, and that ties us into this concept of limits that we've been working with. So to find the slope of our tangent line, we would just find the limit of this as x approaches a. So we're still going to use that same slope formula, but here we're imagining a scenario where our x value is getting closer and closer and closer to our a value until it eventually turns into that tangent line. So we're finding the limit as x approaches a of that same slope of f of x minus f of a over x minus a. So this is how you could find the slope of your tangent line at the point x equals a, which would give us that instantaneous rate of change of our function. So you can see how the concept of limits is really going to be essential to us working with these rates of change. Now here again is that definition of the slope of a tangent line that we just found, and then there's another kind of representation of that same idea. So again, here's the one that we did. Here's the function f of x, and we have a and x, and we have those 2 points. Again, we're just finding the slope between those 2 points, but then instead of the 2 points being here and here, we're imagining that it's a scenario where x approaches a. So again, it's the limit as x approaches a of f of x minus f of a over x minus a, which again is just the slope between those 2 points. Another really common representation of this definition, instead of using x and a, we use a still here, and then we just use this new x value, which we call a plus h. So that's essentially saying that the distance between the 2 points is h. So here you can see that, again, we have the 2 points. So we have a, f of a, and then we have this coordinate, which would be a plus h, and f of a plus h. So again, if we wanted to find the slope between those 2 points, we would just do the rise over run. So we do f of a plus h minus f of a over a plus h minus a. And you'll see that this actually simplifies to just h. But again, I'm just doing y2 minus y1 over x2 minus x1. It's just the slope between those 2 points. But here you can see that, again, since we're finding the slope of the tangent line, we're doing the limit as h approaches 0. So it's essentially saying as the distance between these 2 points, which we're defining as h here, approaches 0. So again, it's that scenario where this second point is getting really, really, really infinitely close to our first one, which will eventually lead us to that tangent line. But again, it's just the slope. So we're still using the slope formula, but we're incorporating that limit to bring the 2 points closer and closer together. So again, both of these are really common ways that you'll see this definition. It's important to know how to interpret and use both forms. All right, let's give this first example a try together. First, we're going to find the slope of the tangent line to the function f of x equals 2 over x at x equals a. Then we're going to find the equation of the tangent line at the point x equals 2. And then we'll sketch a graph of f of x and that tangent line. And for this one, let's use that first form that we talked about, which is listed here. So again, to find the slope of the tangent line at x equals a, we're literally just using this definition. So we want the limit as x approaches a of f of x, and f of x in this case is 2 over x, minus f of a. So I'm just substituting a into our function. So 2 over a over x minus a. So now we just have to evaluate this limit. So you'll notice that if we use direct substitution here, we end up with the indeterminate 0 over 0. So we need to do a little extra work to evaluate this limit. So here we can try combining the fractions in the numerator. So I'll multiply this by a over a and x over x. So we're left with 2a minus 2x over ax times x minus a. And then let's see if we can keep simplifying from here. So the limit as x approaches a of 2 times a minus x over ax times x minus a. So a little trick here that hopefully you remember from maybe pre-calculus. If you have two factors that are opposites, you can make them the same by factoring out -1 from one of them. So let's say we factor out -1 from the factor in our numerator. So it becomes -2 times x minus a over ax times x minus a. Again, I just factored out -1 from this factor. So this became positive x and this became negative x. And then we can simplify this. So you can see that these do cancel out. So we're finding the limit as x approaches a of -2 over ax. And now we can try direct substitution. So if you substitute a for x, we just get -2 over a squared. So this represents the slope of the tangent line at any point, so at x equals a. So again, this is the slope of the tangent line at x equals a, which could represent any point we want. So this is kind of a general slope expression. So now let's move on to the second portion of the question, which asks us to find the equation of the tangent line at x equals 2. So here we are finding a linear equation. So we're going to need two things. We're going to need to find a point on the line, and we need to find the slope of our line. And again, we're finding it at x equals 2. So we can find a point on our line by just simply evaluating f of 2. So f of 2 is going to be 2 over 2, which is 1. So we have the point 2, 1. And we can find the slope of our line using this, which is the slope of our tangent line at any value a. So we can just substitute a with 2. So the slope of our line will be -2 over 2 squared. So our slope is -1/2. And then from here, we can use the point slope form to make our linear equation, which is y minus y1 equals m times x minus x1. So this is a really important formula to remember. We learned it way, way, way back in Algebra 1, but it's popping up again in calculus. So let's substitute what we know. So y minus y1 equals m times x minus x1. So here's the equation of our tangent line when x is equal to 2. All right, the last thing we're asked to do is to sketch a graph of f of x and the tangent line. So for this, it might help to write this in the slope-intercept form, so -1/2 x plus 2. So I'm just going to do a really, really rough sketch here. If you look at f of x, it's a rational function. I can see that we have a vertical asymptote at x equals 0, and we will have a horizontal asymptote at y equals 0. And then we can substitute a couple x values to find a couple of points. So we'll have the point 1, 2, and we'd have the point 2, 1. So it looks something like this, and it's going to travel along our asymptotes. Then I know it's going to do kind of the same thing in this quadrant. And then if we're going to graph this, our tangent line, I know that it goes through the point 2, 1. and it has the y-intercept of 2, slope of negative 1/2, so it looks like this. There you go. So in blue we have f of x, and in green we have our tangent line. All right, let's try another one together. So here we're going to find the slope of the tangent line to this function, f of x equals 1 plus x squared, at the point x equals a. So we're just finding the slope of the tangent line at this general value a. And this time we're going to try to use this form, the limit as h approaches 0 of f of a plus h minus f of a all over h. So again, we're really just substituting just directly into our formula. So the limit as h approaches 0, first f of a plus h. So I'm going to use our function, and I'm just going to substitute x with a plus h. So I'll do 1 plus a plus h plus a plus h squared. So that's f of a plus h. And then we're going to do minus f of a. Be careful here. We are going to be subtracting this entire polynomial. So 1 plus a squared. So again, this is f of a plus h. This is f of a. And all of that is over h. And we're evaluating as h approaches 0. So we can't yet just do direct substitution. So we're going to need to do a little more simplifying. So the limit as h approaches 0 of 1 plus a plus h plus a squared plus 2ah plus h squared, and then minus 1 minus a squared. I distribute that negative over h. So be really careful with this second part of subtracting the entire function. Let's see what we can simplify from here. You might notice that the 1's cancel out, and the a's cancel out, and the a squares also cancel out. So we have the limit as h approaches 0 of h plus 2ah plus h squared all over h. So we can simplify that because we have the common factor of h. So we're left with 1 plus 2a plus h. So the limit as h approaches 0. So from here, we can just do direct substitution. So the h becomes 0, and we're simply left with 1 plus 2a. So this represents the slope of our tangent line at any point, so for any value a. So if we wanted to find the slope of your tangent line at x equals 5, you would simply replace a with 5. So again, when you're finding this slope with the value a, it's kind of creating kind of a general expression to represent the slope of our tangent line. All right, so now we're going to talk about one of the applications of this slope of our tangent line, which is the relationship between position and velocity. So a position function gives you the position of an object at a moment in time, such as maybe the height of a projectile at a given time in seconds. The rate of change, so the rate of change of that position function gives us what's called a velocity function. So velocity is just the absolute value of speed. It's essentially speed with a direction. But again, if you find the rate of change of your position function, it gives you the velocity of your object. And then the instantaneous rate of change, which would be, again, the slope of our tangent line, as we just talked about, for a position function, would give us the instantaneous velocity of our object. So the exact velocity of our object at a specific point in time. Okay, so let's consider the following position function. We have h of t equals 64 minus 16t squared, where h is the height of an object in feet and t is the time in seconds. And here's a little graph, and here's our x and y axis here. It's a little hard to see, so I'll make it a little darker. All right, so let's look at part A. Here we want to find the average rate of change, or the average velocity, of the object between 1 and 2 seconds. So let's just say here's t equals 1 and here's t equals 2. So we're essentially just finding the slope of the line between these 2 points. So that slope of the secant line. So that slope of our secant line we can find by just doing h of 2 minus h of 1 all over 2 minus 1. So that gives us 64 minus 16 times 4, and then minus 64 minus 16 over 1. So our slope of our secant line, well, this just gives us 0, and this gives us 48, so it's going to be negative 48. And here we can give it a unit. So since it's rise over run, the rise is represented in feet. That's what our x-axis or our y-axis represents. And the run would be our x-axis, which is time in seconds. So it's feet per second. So that would be the average rate of change between 1 and 2 seconds. But now let's talk about how we could find that instantaneous velocity. And this means for any a value. So for any value, so we'll just use x equals a. So for this, we want to find the slope of our tangent line. And for this, we could use either the forms that we talked about. So for this one, let's do the limit as t approaches a. So we'll do h of t minus h of a over t minus a. So then we're just going to substitute those values into our function. So that'll be the limit as t approaches a. So h of t is going to be 64 minus 16t squared. And then h of a, we're going to do the same thing but with a. So be careful, we're subtracting the entire thing. And then here we just have t minus a. And then here, if we simplify in our numerator, so the limit as t approaches a, 64, and then we have minus 64 here. So that leaves us with negative 16t squared plus 16a squared over t minus a. So here we could do a little bit of factoring. Don't forget to write that limit every single time. So here, let's factor out 16 or negative 16. So that leaves us with t squared minus a squared over t minus a. And we know this can be rewritten as t plus a times t minus a. So if we simplify a little bit more, you'll see that the t minus a factors cancel out. So if the limit as t approaches a of negative 16 times t plus a. So for this one, we could just do direct substitution. So we'll substitute t with a. So we get negative 16 times a plus a, which gives us negative 16 times 2a, so negative 32a. So again, that's the general instantaneous velocity. So that's for any x value. But now let's see if we can find the instantaneous velocity when t is 2. All we have to do is plug in 2 into this. So this would give us the velocity at 2. So negative 32 times 2. So it'd be negative 64. And then again, our units would be feet per second. So again, here for the average rate of change, we just found the slope of that secant line. And then here we found the slope of our tangent line with a general value x equals a. And then you can use that to give you the instantaneous velocity at any t value you want. All right, so all this stuff we've been doing, finding the slope of our tangent line or finding the instantaneous rate of change of our function. We've actually just been finding the derivative of our function. So that's what a derivative is. The derivative is simply the slope of our tangent line or the instantaneous rate of change of our function at some point x equals a. And we can denote the derivative with this symbol right here. We read this as f prime. So f prime of a is just the derivative at the point when x equals a. So again, all the stuff that you've been doing, you have just been finding the derivative of our function. So there are lots of different representations of this derivative. You can see these first two, we've already covered both of them, and we used both of them to help us find the slope of that tangent line. Same general idea, so essentially you're finding the slope between 2 points where the x values are getting closer and closer together. But just kind of two different representations of that second point. And then down here, again, here we just have an x1 and an x2, and then we call this delta x, which is just change in the x value. Here we call this change of y. So it's really just the limit as delta x approaches 0, right? The difference between our x values is approaching 0. And then here we essentially just have our slope formula again. We could also say it's the limit as x2 approaches x1. And then here's kind of an interesting form that you might come across. This is called the symmetric difference form. So you could see here's our value a, right here, this is a. And then you could see that they went h units to the right and h units to the left. So here's a plus h, and here is a minus h. So we have a point on the right, so a plus h, f of a plus h. Then we have this point on the left, a minus h, f of a minus h. So it's the slope of the line between those 2 points as those 2 points get closer and closer together. So the distance between those 2 points would just be 2h, right? Because h to the right, h to the left. So it's really the limit as h approaches 0. Again, as these points converge on a. So it's kind of getting closer, in this way and in this way. So as h approaches 0, the distance between those 2 points here and here. So not as common of a form, but again, you might come across it. Certainly these first two, you should be familiar with both forms, and you should be able to use both forms to help you find that derivative. All right, so here let's do one more together. Let's find the derivative f prime of a by the limit process. So we're going to use that formal definition, and we're actually going to use both forms, the form with x approaching a and the form with h approaching 0, just for practice for this function. So we're going to just do it with the general value of a. So first, let's do it with this form. So the limit as x approaches a, remember, is of f of x minus f of a over x minus a. So we'll start by doing it with this form. So the limit as x approaches a, f of x we can see is the square root of 3x plus 1. And then f of a would just be the square root of 3a plus 1 all over x minus a. So now all we need to do is evaluate this limit. Unfortunately here we can't just do direct substitution because we would end up with 0 over 0. So we'd get an indeterminate. So we do need to do a little bit of extra work. First we can try multiplying by the conjugate. So we have the square root of 3x plus 1 plus the square root of 3a plus 1. And I know this looks really ugly, but it will actually simplify out pretty quickly. So our limit as x approaches a, if we multiply out our numerator, our first term times our first term just gives us 3x plus 1. And then our second term times our second term, or our last times our last, so we have minus 3a plus 1 all over x minus a. times the square root of 3x plus 1 plus the square root of 3a plus 1. So you can see in our numerator, the 1's cancel out, and we're just left with 3x minus 3a, so we can actually factor that. And when we do, so we have 3 times x minus a, you'll see that there's that common factor of x minus a. So we're left with 3 over the square root of 3x plus 1 plus the square root of 3a plus 1. And from here, we can just do direct substitution to evaluate our limit. So it'll be 3 over square root of 3a plus 1 plus the square root of 3a plus 1. So again, I'm just substituting x with a. And then these, since it's the same, they have the same radicand, we can actually just add them up. So this will actually give us a final answer, which will be our derivative. So we'll say f prime of a equals 3 over 2 times the square root of 3a plus 1. So finding that limit is definitely a little bit tedious, but that's really the hardest part, is actually evaluating the limit. Really finding the derivative is just plugging it into a formula that we should eventually have memorized. So now let's do the same process, but with the other form of our derivative, just to make sure we can get the same answer. So the limit as h approaches 0 of f of a plus h minus f of a all over h. Remember, it becomes a plus h minus a, so just the h. So here we have the limit as h approaches 0. F of a plus h gives us the square root of 3 times a plus h plus 1 minus f of a, which is the square root of 3a plus 1 all over h. So for this one, we'll have the limit as h approaches 0. We do need to do a little extra work to evaluate this, so we can multiply by the conjugate again. So we have the square root of 3a plus 3h plus 1 plus the square root of 3a plus 1, and multiply by the same thing in the denominator. All right, so this gives us the limit as h approaches 0 of 3a plus 3h plus 1 minus 3a plus 1. So again, the first times the first and the last times the last with the subtraction. And then we have over h times the square root of 3a plus 3h plus 1 plus the square root of 3a plus 1. Let's simplify a little bit. So here, 3a and 3a cancel out. 1 and 1 cancel out, and that leaves us with 3h over h, so the h's will also cancel out. So the limit as h approaches 0 of 3 over the square root of 3a plus 3h plus 1 plus the square root of 3a plus 1. And then from here, we can just do direct substitution. We'll replace all of our h's with 0. So essentially, this just becomes 0. And we end up with 3 over 2 times the square root of 3a plus 1. So it's the exact same answer that we got with our other form. But again, it's really important that we can work with both forms and that we understand how to interpret and use both forms. So this is our derivative of this function. All right, here's the last example that I'd like you guys to try on your own. So please pause the video and see if you can find the derivative using both of the forms, just like we did in the last example. All right, go ahead and check your work here. So here you can say I did both methods. For that first method, when x approaches a, here's the substitution. To simplify this, you need to get a little creative. So I see that there's this x minus a in the denominator, so I want to find some way to try to create that factor in the numerator. So if you rearrange the terms and you put your squared terms next to each other, and then these terms next to each other, you can factor this using difference of two squares, and you can factor out a GCF of 2, and then you'll see they have that common factor of x minus a. So from there, you have x plus a plus 2 remaining, so you could do direct substitution here. So you get a plus 2, which is 2a plus 2. So that would be f prime of a. So that's our derivative. And you could find the same result with the other method. So again, here's f of a plus h minus f of a. And then you just need to multiply it out and really cancel out common terms or opposite terms. And then from here, you can do direct substitution. Again, you replace h with 0, and you're left with the same thing, 2a plus 2. So that would be f prime of a. So I know these do feel a little bit tedious at first, especially plugging through, but if you kind of show out your steps and you just stick with it, you'll find that they do actually simplify out a lot quicker than you think. So don't give up when you get started, just keep plugging through and you will make it to the derivative. All right, so that is all for today's video. Thank you guys for watching.